Okay, there's Jonathan. All right, we're going to talk about work and energy relationships today. You might remember last week I said, well, I could start this in the 5 minutes we had remaining, but it's a whole new topic. It really wouldn't have done us much good. So here we will start. So in class, that is in the general physics class, we were given the equation that work was equal to force dot delta x. Now, this being a calculus class, we can already make a guess that that delta x, in calculus, deltas are converted to d's. And so that in calculus, it's an integral. So the work going from A to B is the integral from A to B of force dot, and I put here dr. R is one of a few symbols that are used for a three-dimensional position. So that dr just means, and I have this shown in a few slides, dr vector is x hat dx plus y hat dy plus z hat dz. So it has the three components. One of the things that is important is if we are going to define a potential energy, this equation for work is the equation for work. It's simple. If we're going to define a potential energy, we have to have a special rule about the force. What was that special rule about the force?
Conservative.
It has to be conservative. So potential energy is defined as change of potential energy is minus work conservative. And so I gave you kind of a nebulous hand-waving definition of what a conservative force was in the general physics class. That is, I said that a conservative force is a force that you do work on it and it will give you back all of the energy that you put into it when you did work on it. There's a mathematical way of defining a conservative force that looks nothing like that definition. And so I'm going to write it here. We're going to explore it later. But for a conservative force, the curl of the force, okay, because of the energy thing, that didn't come out as well as I wanted. I'll write it up here. The curl of the force is 0. And I'm actually going to work this out later on. Is there anyone who is actually familiar with the word curl or this meaning gradient cross with F? A little bit. A simple way of thinking about this is that if you start somewhere and you integrate your force on any path that comes back to your starting point, it always has to integrate to 0. That's a simple way of thinking about this. That's what the curl equals 0 translates to. So you could also write this as an integral over a loop of force dot dr equals 0. Those actually mean the same thing mathematically. It's just a different way of getting there. You can transform from one to the other. So that's a condition on a conservative force. And this is going to be important for the last part of today's lecture. But for starting today's lecture, I just want to show how we can calculate the work and then the potential energy for 3 different conservative forces. So I have the 3 different conservative forces here. The force for a spring that we've seen before. Force of the spring is proportional to how much you stretch it. So this x vector is the amount you stretched it, minus because when you stretch it, it tries to pull it back. So that minus means it's restoring. The k is just a constant. Force of gravity, the easiest one to work with because it's just constant in direction and magnitude. And then the real force of gravity. What kind of silly teacher says the force of gravity and the real force of gravity? Especially when, after Einstein, one would have to argue that this isn't the real force of gravity either. This is Newton's form for the real force of gravity. It is indistinguishable from Einstein's form for most situations, for any situation that we're going to encounter in our lives. But there is a difference in Einstein's gravitation and Newton's gravitation. This is Newton's universal gravitation equation, that the force is the minus r hat is to tell you direction, g mass 1 mass 2 over separation squared. And I think we had this before. The second form is just an alternate way of writing, showing r vector instead of r hat and putting over r cubed. So we're going to work with each one of these forces and get started right now. So my definitions for work and change of potential energy at the top of each page here. And then I have the force I'm going to work with, the force for a spring. Now I'm going to start out by making a graph of this force. So the force of the spring, here's going to be my position. The force of the spring in newtons. And of course, I made this so it's going down because of the minus sign. And so I would have a straight line relationship here that has an equation of the magnitude of this force of spring is equal to minus k magnitude of the x. Okay, the minus sign is because it's a negative function. I said magnitude. Magnitudes obviously don't have a sign, as we had on the test question. But bear with it. So there's what it looks like. What did we learn in class that we could use it, how we could use a graph to find the work done?
Using the slope.
Not using the slope, but it's an answer. The what? Not the y-intercept. The area. The area under the line. Well, in this case, the line is below 0. So the area is negative. But if we calculate the area, so if I go from here to here, from x1 to x2, then the work done by the spring is going to be the area I get for this. Now I can calculate that area by breaking that into two pieces, one that's a triangle, one that's a rectangle. And so the area here is equal to the force when x is equal to 1. So that would be minus k x1 times x2 minus x1. Right, that's the area for a rectangle, base times height. Plus for a triangle, 1/2 of minus kx1 minus kx2. That's going to be the average. Well, actually, that's a bad plan. I shouldn't have done that. I wasn't thinking. For this triangle here, the additional increase is going to be minus k times x2 minus x1. That's how much it increased for the initial, or for that. And then, of course, and my 1/2. So if I put those together, multiply everything through, I will get my equation for the area. And I have x1 and x2 in there. I'm not going to actually do it right now. I'm going to use calculus to do it, and then we'll compare the two. So that's how I would get at finding the area underneath. So just in case people weren't catching this, this was the base, change colors. This was the base of the triangle, or excuse me, the height of the triangle. And this was the base of the triangle, and then the 1/2. So the bottom part's the triangle. The first one was the rectangle. Now, if we do it calculus method, to me it's easier doing the calculus method. I would have work going from x1 to x2. My force dotted with my dr. In this case, that's going to be dx because my r vector is only in the x direction. Now, when I have a dot product, what does the dot product mean?
Only multiplying the parallel.
Only the parallel parts. So I have here x vector, which is in the plus x direction. I have dx vector, which is in the plus x direction. Those are the same direction. So this is equal to, let's bring out the constants, minus k. So there I applied the dot product, which because they were the same direction, just dropped the vector signs in the dot. It's easy if they're parallel or perpendicular. If they're somewhere in between, then we have to do a little more work. So now everyone here can do this integral, right? So we have our constant out front, minus k. Integral of x dx is x squared over 2. And then we have to put our limits on this. So there's my equation for the work, or putting it in the, you might say, why didn't you just make that minus a plus? And the reason is because I want it to be in this form. So there's my equation for the work done to go from position x1 to x2. Now let's compare that to what we had for the area, just to make sure that the area was right. So if we multiply through on that area, I'll have minus k x1 x2 plus k x1 squared. So that's the rectangle portion. And then I'll have plus, and I'm going to put the 1/2 first now. There's a minus k out front, so I actually should have just put a minus here, minus 1/2 k. And then I have x2 squared minus 2x1 x2 plus x1 squared. If I look at these, I have minus k x1 x2, and here I have minus a minus, so plus. So this here and this here combines to give me plus k x1 x2 over 2 times 2. So those are going to add out to 0. I like to do my adding out to 0 as quickly as I can. And so I'm going to have kx1 squared minus 1/2 kx2 squared minus 1/2 kx1 squared. Or simplifying further, I have minus 1/2 kx2 squared plus 1/2 kx1 squared. Why plus 1/2? Because I had kx1 squared and minus 1/2 kx1 squared. Is this here the same as this here?
Yeah.
Yes, good. That means either method worked. I'm not going to find the area on any of the others because they're not as easy as this. Well, actually, force of gravity is even easier. Got to take that back. Why did I do it in this form that you see right here? Because we know that we define change in potential energy is equal to minus the work, which means it's potential energy, well, minus potential energy final, minus parenthesis, minus potential energy initial. Right, since I did that wrong because I'm not thinking. Potential energy final minus potential energy initial because it was change in potential energy. But if I do work, I'm going to have to change the signs. So that means work should equal minus potential energy final minus parenthesis minus potential energy initial. And so if we compare these two directly, you see that this here must be this here. And this here, well, let's not use the same color. This here must be this here. And so we can define potential energy due to gravity is equal to 1/2 kx squared. Now in this case, there is a specific reference point for x. X is 0 when the potential energy is 0, which is when the spring is unstretched. So our potential energy is 0 when x is 0 is built into this. You don't have an arbitrary choice for where you can put 0 potential energy for a spring. But that's how we calculate the potential energy equation for the spring. So I've done all the work here. Do I have any questions about that work? I assume this doesn't mean I have a question. Okay, the next one. Now we're going to do the force of gravity. If I did a graph of the force of gravity versus distance, what would that look like?
Exponential.
Not with this function, it won't. With this function here, force of gravity equals mg. Where's distance in that equation? It's not. So the force of gravity here is just going to be a constant. Since it's minus mg, it's down here. I'm not even labeling the axes. It's pretty simple. So if we want to find the work going from 1 to 2 is equal to integral from x1 to x2 of my force of gravity minus mg y hat dot dr vector. Well, let's go ahead and define our dr vector. Let's say that we're going to go from x initial equals 5 to y initial equals 10. Well, take that back. Let's make it more general. We're just going to go from x initial, y initial, z initial to x final, y final, z final. So we're going to go from our initial components to our final components. Question?
Are we subtracting C final from that, or just this?
Are we subtracting what?
You put like a minus sign.
Oh, that's supposed to be a comma. That's a mistake on my part. Thank you. Okay, so when we do this integral, I'm going to put my dr here explicitly. So this is integral, and I should have put here R1 and R2. And since I changed it to initial, final, there we go. So I've explicitly put in my 3 dimensions for dr. But we're doing a dot product. The dot product means, and I've done this a lot of times, just making sure people are following along. A dot product means I'm multiplying which 2 parts of my vectors? The parallel parts. So if we look at this, I have the force is all in the y direction. So how much of the x direction is parallel to the y? None. How much of the y is parallel to y? All. How much of the z is parallel to y? None. So this collapses to a really simple integral when you do the dot product. This will become, bring the constant out front, minus mg integral from r initial to r final of dy. What happened to the dx and the dz? There were zeros for those. So now I have my r, which is x initial, y initial, z initial, but my integral is only dependent on y. And so when I do this integral, forgot the minus sign. I have that. Why is there no x in it? One last time.
That's not parallel.
It's not parallel, it's perpendicular. So now we can take this and we can take it and put it into a real situation. Let's take the problem with Carlos hiking up the mountain. We have two different options. One, the x and z, since I call y vertical here. The x and z are going back and forth, back and forth, back and forth, while the y is slowly going up. The other one, x and z stay at 0 while the y is slowly going up. Since x and z don't play into this, there's no difference in the calculation here. It's only the difference between y initial and y final that's going to matter. It doesn't matter what path he takes. He'd go up and down and all around. As long as he starts at point A and ends at elevation point B, that's all that's going to matter is the difference in elevation. So the path doesn't matter. That's part of a conservative force. Another way of defining a conservative force is it does not matter what path you take. The work only depends on the starting and ending points. So in this case, going back to our potential energy function, change in potential energy equals minus work. So if I look at this equation, I must have potential energy is equal to mgy. So you can see where that equation came from. It was a very simple calculation. These first two were not so difficult. The last one is a more difficult, although it's not going to stretch you. Any questions about how I did this with gravity? Now,
Should there be a negative on MGY there?
no, because going back to the previous one where I wrote it down, the work should be minus potential energy final minus a negative potential energy initial. So that's why I have it with the negative in parentheses, parentheses negative, so that we see yes, it's minus and then the potential energy final. Now with potential energy due to gravity, we can freely put any offset on it. If you actually look in the pre-lab, I think in the pre-lab I might have really waxed eloquent and talked about why you can use any offset you want for your 0 point with gravity and not with the spring. But suffice to say, because the force of gravity is constant, is a reason why we can have that offset without any difficulty. So, do I have any questions at all on this? Okay, let's go to the third and final of our forces we're going to calculate a potential energy for. The force of gravity using Newton's law of universal gravitation. Now, if I make a graph of this, notice if r equals 0, I'm dividing by 0, which means it's going toward infinity. So I'm going to have a graph, force on this side going down toward minus infinity here. Separation in meters here. And as r approaches 0, it's approaching minus infinity. And then we have our nice, 1 over r squared curve for what happens as r gets bigger. And it asymptotes to 0. So if I have two masses infinitely far away, the force between them is 0. The closer they get, the stronger the force is, and it's always attractive. So now, remember I said we could find the area. Well, how do you find the area of this thing? You do it with calculus, that's right. You don't sit there and try to fiddle around and draw shapes to fit it. You do calculus. That's why Newton invented calculus. Because you can't fiddle around and make shapes and make it work out nicely. So we'll just do our calculation. The work due to gravity is equal to integral that's a G. I swear I changed it when I took this slide and used it for yesterday, which we never got to. Left it like this for today. So I have minus G M1 M2 over R squared R hat dotted with dr. Now notice r is the distance of the separation. It's only going to matter how far away they are from each other. It's not going to matter if I go around in the circle, because going around the circle is not going to change the r value at all. And the force is always going to be in the r direction. So this, because r vector and dr, this is always going to come out to be minus G M1 M2 integral of that. Now I said this is the hardest one, but that's not taxing. What's the integral of dr over r squared?
Negative r, or 1 over r.
Negative 1 over r.
Yeah.
So I had minus G M1 M2 times minus 1 over r. So if I plug in those limits, notice there's a minus and a minus now. So it's going to be a positive. Steve. Okay, went away. Hopefully it won't come back. I sneeze really loud, so I'm trying to save you, your ears. So there's my work calculation. Now let's look at this work function and compare it to the force. What's different between that function and the force function? Yeah. It was r squared, 1 over r squared, what we call an inverse square law for the force. The potential energy is just 1 over r. Now, if you didn't know calculus, you would tend to think, oh, so we just took 1 over r squared and we multiplied by r and we got 1 over r. Makes sense. But no, we didn't multiply by the distance, we didn't multiply by the distance between the two. We did an integral over the change in motion. Two distinctly different things. And so it's not that simple, but it looks that simple. Another difference is the sign changed. It was an attractive force, so it had that negative sign in the vector form. Now it's positive, but remember, this is equal to minus potential energy final minus potential energy initial. So that means this gives us potential energy is equal to minus G M1 M2 over R. I usually use a capital G to mean using Newton's universal law of gravity that has a capital G in it. I use lowercase g if I'm using mg, which has a lowercase g in it. So this is my potential energy equation. Things to note here. What value of R gives you the maximum possible potential energy? It's kind of a trick question, I'll warn you. What value of R gives you the maximum possible potential energy? It's 0.
Well, maximum would be, I mean, it's going to be negative, isn't it? Oh, wait. No.
Or wait, I'm wrong. It's infinity. Yeah, it's infinity because it's going to be a potential energy of 0. I got myself confused. See, it's tricky. So at R is equal infinity or approaching infinity, the potential energy approaches 0, which is the maximum value. For any finite R, your potential energy is negative, so it's lower. And as R approaches 0, as they get really close, the potential energy goes way, way up. And so we've actually passed over the part on planetary orbits. But planetary orbits, you calculate the total energy. Total energy is kinetic energy plus potential energy. And so for a planetary orbit, energy is kinetic energy plus potential energy equals 1/2 mass times speed squared minus g over R. Now, I should have put M1s there. Just you have two masses involved. You have to know which mass is which. That's the equation for the total energy of a planet orbiting the sun, let's say. So in this case, M2 would be the mass of the sun, M1 would be the mass of the Earth, and the energy of the Earth orbiting the sun is given by this equation. If that energy is negative, then the Earth can't escape from the sun. But if you make it go faster, you're going to increase the kinetic energy. It will then move farther away. And if the energy gets up to 0, so if you have enough kinetic energy that if you put all the kinetic into potential energy, it would get to infinitely far away, then it's free to leave. So as long as you have negative total energy, it's bound. If you have 0 or higher total energy, it's free. Now, most of you have never worked with planetary orbits, and that's like, oh, gee, that's a new thing. But think about how many people have taken general chemistry. Okay? You've learned about electrons being bound to a nucleus. The electrons are bound to the nucleus not with gravitational force, but with the let's just say electromagnetic force right now. That force, the electromagnetic force, has exactly the same form as gravitational force. The difference is gravitational force only comes with one kind of charge, positive mass. Whereas electric force comes with two kinds of charge, positive charge and negative charge. We call it charge with the electrons, we call it mass with force of gravity, but it's still the charge associated with the force. And so things are a little different, a little more complicated, but you still have the same rule. When you learn about the energy states for an electron and a hydrogen atom, you have the ground state, right? It's 13.6 electron volts. How much energy do I have to put in to ionize that? 13.6 electron volts, so I can raise the energy up to 0. If I raise the energy up to 0, then the electron's free to go. If I put in any energy less than that 13.6 electron volts, they'll still have a negative total energy, and the electron remains bound. So it's the same principle, just a different force. And if we have enough time, I'll come back to this. But I want to do one more thing, actually, if we have enough time. We're not going to have enough time, I can tell you. Last thing. We've gone now from force to work to potential energy. We can reverse that process. We can go from potential energy back to force. And so I wrote up here the equation for minus change in potential energy. I put the definition of curl, and I put the definition of the gradient operator. And now I want to show the relationship. So what is the gradient operator? It's a directional derivative. What was my equation for work? It was a directional integral. Well, what did you learn in calculus was the relationship between an integral and a derivative? They're what? They're pretty much inverse functions. The fundamental principle of calculus is the derivative with respect to x of the integral with respect to x of force of x has to be the force of x. Right? That's your fundamental principle of calculus. And so there should be a relationship between integrating and taking the derivative to get me back to force. Right? Since potential energy has to do with integral of the force, I should be able to take a derivative of my potential energy and get back to force. Now, what is that? I'm going to start with the answer. The answer is the gradient of the potential energy is minus the force. Now, I had a student who's taking the kinematic, thermodynamics, physical chemistry, P-Chem. It's called physical chemistry because you're actually looking at the underpinnings of chemistry, which is physics. So, she was, how does that work? So I want us to look at this and see how it works. So if we do del of the potential energy, that's going to be del of minus the integral of f dot dr, right? Because of our definition that we had change in potential energy was equal to minus the work, and the work was equal to integral of f dot dr, so that's equal to minus integral. Now, I did one thing that's a little loose. I dropped off the limits here, and instead of putting, delta P, I just put PE here. So the gradient of potential energy is minus the force is our answer, and we want to see that this works out. We're not doing the mathematical proof of getting there. We're doing the mathematical check to see if it's correct. So if I do the directional derivative here, I'm going to expand what f dot dr means. So F, and I have this actually written out here, F is the force in the x direction, x hat, plus the force in the y direction, y hat, plus the force in the z direction, z hat. Right? That's just breaking it into its components. And you've all learned how to do that with triangles and trigonometry. And then the dr is dx in the x direction, plus dy in the y direction, plus dz in the z direction. If I do the dot product between the two, what's going to happen? Only the parallel parts are going to be non-zero. And so if I do that dot product, I'm just going to write them as three integrals. Integral of fx dx plus integral of fy. Let me put the minus sign out here so I don't have my signs wrong. Dy plus the integral of fz dz. Now I have to use what my gradient operator means. So let's just take this portion right here. I'll just do that portion first, and then we'll, by analogy, do the other two portions quickly. So I'm going to have that portion is minus x hat d dx plus y hat d dy plus z hat d dz acting on the integral of f of x dx. Now, since that integral is only of x, only a derivative with respect to x is going to even care that there's an integral sign. The derivative with respect to y, the derivative with respect to z, that can go right through the integral sign because it's different variables. What does the derivative with respect to x do to my integral with respect to x? The fundamental theorem says, well, those are just going to cancel each other out. So that for the first term, I'll have negative f of x in the x direction. For the next two terms, I'll have minus the integral of derivative of f of x with respect to y dx in the y hat direction. So I'll put the y hat out front. And then minus z hat integral of df of x dz. So that's what I get from the first one. Now, if I do the second one, by analogy, I will have the y term is the one that's just going to bring out the f of y. Go ahead.
Your line above your two integrals, you ended with the dx and then the dz. Is that right?
This one here is the one that has a mistake. Is that the one you were looking at?
I just figured one of them.
Yeah, that's the one that had the mistake.
Okay.
Thank you. So by analogy, it's the y term that now comes out for the second one. And then I'll have minus x hat integral of df of y dx dx minus z hat integral of df of z did I get my I need to pay attention. No, I was wrong in the one that was wrong. This was looking at only the x, so those were like that. This here is looking at only the y. Okay, so that's that one. Maybe I shouldn't have gone so quickly.
Dr. Webb,
Yes.
how did we get the x hat in the shut?
As soon as I finish writing this, I will answer your question. Okay, I think I wrote those all correctly. Right, this is the first one was f of x dx, so that's why it had to be dx for all of them. Okay, the question that you asked me was, how do we get the y hat, the x hat, and so on, right?
But so your last one is still an x hat.
Should that second term be z?
Yeah, is that
This one here,
yeah.
this is z. These should be x hat and y hats. This one here is z hat out front. Okay, where they come from is I have x hat ddx. So the one with the ddx needs to have an x hat out front. The one with the ddy has to have the y hat out front. The one with ddz has to have the z hat out front because those were part of my gradient operator. Now, if you look at this, you realize right away that these things right here add up to give me minus the force vector. Minus sign because they all had a minus. Forces of x in the x direction plus force y in the y direction plus force z in the z direction. So what about those other things? What gives with those? Well, here's what gives with those. If we look at our curl relationship, we had for conservative forces, that curl is equal to 0. How many people are familiar with cross products? Okay, good. That's at least half the class. The other half of the class, this is new. A cross product, also known as a vector product, is multiplying the perpendicular parts of the vectors. So the dot product was the parallel parts, the cross product is the perpendicular parts. Notice we use that cross sign to be multiplication if it's scalars. We also use the dot to be multiplication if it's scalars, because they both mean multiplication. But if you have vectors, the dot is a specifically different kind of calculation than the cross. So that's why when you're doing cross products and dot products, it's really vital to have vector signs or your mathematical notation means something different. So to multiply the perpendicular parts, we have a determinant rule for doing the calculation. That determinant rule is you put your x hat, y hat, z hat. So that's the first row. The second row is going to be the components of my gradient. So the components of gradient were in the x direction, it was d dx. In the y direction, it was d dy. And the z direction, it was d dz. And then for the final one, I'm going to put the components of the second part of the cross product. So that would be fx, fy, fz. And now we do the determinant. Determinants, when I was in high school, I learned two rules of doing determinants. When you're doing this, you have to use one of those two specifically. And that one you have to use is you choose a row or a column, and you take each element multiplied by the Levi-Civita symbol multiplied by the determinant of its comatrix. All that said is probably more confusing than doing it. So let's do it. So I'm going to take that row. And so I'm going to start with x hat. The Levi-Civita symbol actually has a symbol 1, 1, 1, or 1, 1 in this case, because it's only two dimensionals. And the Levi-Civita symbol, all it does is it alternates sign. So 1, 1, the Levi-Civita is just 1. 1, 2, it's going to go to -1. 1, 3, it's going to go back to +1. It just alternates signs. So let's not worry about trying to learn the Levi-Civita symbol. We'll just learn it's going to be plus, minus, plus for those portions. So I have x hat multiplied by the determinant of its comatrix. The comatrix is the matrix I get if I cross out the row and the column that I'm looking at. So that leaves those two. The determinant of that, I have to do the top one, bottom one. So it's going to be d dy of fz minus d dz of fy. So that's the first term in my cross product. That's my x component of the cross product. So now I go to the second one. And so I'll have minus y hat, minus because of that alternating signs. And then I have my comatrix is going to be taking out this center row, so it's going to be d dx fz minus d dz fx. And then my final row, back to plus, because of the third one now. And the comatrix is now the two on the left, d dx of fy minus d dy of fx. So that whole thing, if it's a conservative force, has to equal 0. If that equals 0, that means the x component equals 0, and the y component equals 0, and the z component equals 0, right? If it's equal to 0, all three components have to be 0. And so I now can make from this a relationship that dfz dy must equal dfy dz. And likewise, dfz dx must equal dfx dz. And finally, dfy dx must equal dfx dy. So I have those three relationships that came from the demand that if I have a conservative force, the curl is 0. So now let's take these and go back and look at these. Integrals with respect to x, I had, where are they? Yeah. So the this here dfx dy has to be equal to this dfy dx. I didn't put this all together beforehand because I'm looking, I'm like, but what we're going to end up having when we take these together with my three rules on what's equal to 0 is that I end up with this whole thing coming to 0 because of that curl relationship. Yeah, honestly, I thought, oh, with this curl relationship, it's going to be obvious. Now I look at it, it's not quite as obvious as I was thinking, but that is why you can do it. So the end result of all of this is that you can find the force by taking del, the gradient of the potential energy, and the minus sign. Okay, we're out of time. How convenient. Any questions you want to ask before you walk out the door? Okay, there's one problem on the homework assignment that's due tomorrow that has you integrating a force. So you're going to be doing something akin to these three calculations here on the homework that's due tomorrow. And I'll probably give you another calculus one on the homework that's due on Friday that has you do the reverse, has you use this here. So you can get some practice with it. All right, I'll see you for lab.